Good morning, everyone. My name is Kosei Toyokawa. I'm a PhD student in the Graduate University for Advanced Studies in Japan. Introduction. Since Apple program, for 40 years, the moon had been thought to be lack of water. This is one of the biggest evidence for the giant impact hypothesis. However, recently, water has been detected on the moon following the development of remote sensing and sample analysis techniques. Accordingly, lunar formation and evolution processes are being reassessed. In this study, we investigate the water in a lunar primitive rock outcrops. Purest anorthosite called PAN is rock consisted of 98 volume% pleasure clays. The near-infrared spectrum of the PAN outcrops are like the upper figure, and it shows deep absorption at 1.25 micron, which is attributed to a pleasure clays. And the PAN outcrops are identified at these blue points in this figure, blue points on the moon. The rate of PAN formation is still controversial. Some groups suggest that the PAN layers were globally formed during the lunar magma ocean crystallization, but some other research groups suggest that PAN was formed more locally by magmatism soon after lunar magma ocean. Regardless of the process, the PAN is thought to be formed during the early phase of the moon. So far, water has been, at some PAN outcrops, water enhancement has been detected by spectral data of M-cube and IIRS. This is an example of M-cube data for PAN outcrops showing deep 2.8 micron band absorption of water, the orange and the red spectra. However, the origin of water in PAN outcrops has not been revealed. Specifically, whether the water is of solar wind origin or indigenous origin. So the purpose of this study is revealing origin of the water in the PAN outcrops. If the water in PAN outcrops is of solar wind origin, the water enhancement in PAN outcrops suggests that pleasure clays absorbs water more efficiently than mafic minerals. If the water is of indigenous origin, the water in PAN outcrops is likely to be that of the early moon. So the origin of water in PAN is the key to understanding water supply process on the moon. To understand the origin, the temporal changes of water contents are keys. Short-term temporal change of water content on local time is an important key. Weakly absorbed solar wind origin water is thought to be thermally unstable, so that the water content is decreased for the local noon. On the other hand, the indigenous origin water is thought to be thermally stable, so that the water content should be independent of local time. In addition, long-term time variation is also important. For example, solar wind origin water might experience the process of trapping by micrometeoroid impacts, so that older surface might show more water. On the other hand, such tendency is not expected for indigenous origin water. Rather, the indigenous origin water might be diffused by micrometeoroid impact, so that the water content might be less in older surfaces. It has been suggested that M-cube data have problems of uncertainty of thermal correction. So in this study, we used the spectral data obtained by SELENE, which has large SN ratio for various local time. We try to detect water by the weak 1.5 micron bands, which is not affected by thermal emission. And then we investigate temporal changes of water in pan outcrops for short and long timescale. Methods. SELENE is a JAXA's lunar orbiter, and which conducted observation from 2007 to 2009. Spectral profiler, so-called SP, is visible to near-infrared spectrometer on board SELENE. The wavelength range was 0.51 to 2.6 micron, but we used only the range of 0.51 to 1.65 micron because the longer wavelength range is too noisy to interpret. The wavelength resolution and the SN ratio of SP data are known to be the highest of all orbital spectrometer. So SP data is suitable for the detection of the weak 1.5 micron band of water. In previous study, Yamamoto et al. 2012 mapped the pan outcrops based on SP data. These white points shows the locations of the pan outcrops. And we further extracted less noisy data to detect the weak 1.5 micron band of water based on this criteria. Consequently, we investigate the data for these yellow points. First results, pan spectra with 1.5 micron absorption band. About 3% of investigated data for pan outcrops showed band depth larger than 0.7%, around 1.5 micron. Note that the calibration error of SP data is 0.4 to 0.7%. This is an example of SP data. This is continuum removed reflectance for central peak of Jackson crater. And blue spectra shows the raw reflectance data, and orange curves shows the smooth reflectance. And you can see the absorption feature at 1.25 micron attributed to plagioclase, and at 0.9 micron attributed to pyroxene. In addition to them, you can see the absorption around 1.5 micron with band depth of 1%. This is a histogram of absorption wavelengths for 1.5 micron. You can see that the absorption wavelengths were distributed around 1.55 to 1.58 micron. And there was no absorption at 1.4 micron, which is generally seen in hydrated minerals. This is a global map of band depth of 1.5 micron. And it's difficult to see, but yellow and light green and blue plots shows the higher band depth of 1.5 micron. And the data which shows higher band depths were detected at various latitudes. First discussion, does the 1.5 micron band represent water? Firstly, the calibration error of the SP data is from 0.4 to 0.7%, but we identified absorption larger than 1% at maximum. And secondly, we saw rough consistency between SP data and M-cube data. More than 90% of pan outcrops showing 1.5 micron band in SP data also shows absorption 3 micron band in M-cube data. Thirdly, we identified that the wavelength absorption wavelength is longer than that of general hydrated minerals. This tendency has been reported by previous studies describing the result of Chandrayaan-2, and they argued that for plagioclase-rich regions, the wavelength peak of absorption peak for 2.8 micron is shifted toward longer wavelengths of 3.0 micron. So this is consistent with our result. Therefore, we think the identified 1.5 micron band is likely to represent the presence of water. Second result, temporal change of 1.5 micro absorption band. This is the result against local time. The horizontal axis is observation local time, and the vertical axis shows the band depth of 1.5 micron. And you can see that the absorption was detected even around local noon. This suggests that there is water, thermally stable water, which is consistent with indigenous origin water. And next, I will show the tendency against long-term exposure age. Most outcrops are so small that the crater chronology to use. So instead, we use the spectral slope as an indicator of the relative exposure age, because due to the space weathering, all the surface shows relative spectrum. This is the result with respect to spectral slope. The horizontal axis shows spectral slope, and the right side shows all the surface, and the vertical axis is band depth. And you can see that the band depth values varies for similar spectral slope, and also the maximum value of band depth for each similar spectral slope is smaller for all the surfaces. This suggests that the maximum water content is smaller for all the surfaces, which is consistent with indigenous origin water. Next discussion, the origin of water in palm outcrops. We identified the tendency that the maximum water content is decreased for all the surface. And this suggests that all the surface have less capacity of water. In other words, it suggests that water dispersion during space weathering occurs. This implies indigenous origin water's existence, and this can be evidence of the water removal. Because of time, I skip these slides. In summary, we detected the 1.5 micron absorption band of water in SP data for palm outcrops. Based on the temporal changes, the water of indigenous origin water exists in the palm outcrops. This result supports that the water was abundant in the early phase of the moon. Thank you for listening.
Do we have any questions?
Next time. Hi, Roman Tortes, University of Manchester. Analysis of Apollo samples have shown that it's really, really hard to put water in anorthosites, like more than a few parts per million becomes very hard. So what quantities of water are you suggesting here?
Yeah, that's a good question. That's what I'm working on now. And from the absorption of 1.5 micron, it's difficult to evaluate the water content for now. So I'm trying to estimate the water content from M-cube data obtained in local noon, in order to separate from the solar wind regime. So yeah, but from M-cube data, we can estimate that 100 ppm water can exist in palm outcrops. So it might suggest that abundant water can exist in magma. So yeah, like that.
Thank you. Thank you for your great talk. And could you go back to the slide that you skipped for the interest of time and discuss a bit more? What was the point about?
Thank you. In this study, this is about how does the water exist in palm outcrops. And in this study, we cannot distinguish whether water in palm outcrops exist inside plagioclase or outside plagioclase. If water exists in plagioclase, the crystal structure, as I mentioned, identified absorption wavelength was longer than the general hydroelectric minerals. So if water exists in plagioclase, its crystal structure might cause the wavelength shift. And if water exists outside plagioclase, there might be hydroelectric minerals showing the shift, such as epidote, which is found a lot in terrestrial anorthosite outcrops.
Thank you.
Thank you.